Now, continuing straight on. So we have a string. Now we're assuming the language is regular. Okay, it has a machine M that recognizes it. We assume the string. There are strings in that language. String, let's say string S, that has a length larger than the pumping length, little p, and we set little p equal to the number of states in the machine M. Right? And we're now trying to show that that string S can be split into the three parts, x, y, z, that satisfy the three conditions. Now you may ask, well, what happens if there are no strings that are longer than p, greater or equal to p? Well, convince yourselves. I don't give you a lot of homework lately, it's been a lot more theory, but convince yourselves that in that case, if there aren't any strings, then the whole thing becomes rather trivial. So do that. Alright, so let's start on the guts of the theorem, the lemma, the pumping lemma. So take a string S that belongs to language A regular language, okay, and assume that S has length at least p, okay? At least p, so greater or equal to p. So if n is the size of your string, so if two vertical lines S in the middle equals n, so the length of your string will be greater or equal to p. Now in fact we'll use that a bit further on, okay? So assume that your S has at least length p. In other words, the number of states in your machine M. Okay. Now this string now, imagine it's being processed. It's going through the machine. It's being read. Its symbols, its individual symbols of the alphabet, are being read one by one. Okay. And this machine, as a result of reading each symbol, it's going through, changing its state. And I guess we're assuming it's a DFA. So as we read through each symbol in the string S, this machine will go through a sequence of states. Right? So it'll start with its start state, and that was Q1, because we're given the formal specification of this machine M. And its start state was Q1. Okay, so it starts in Q1, start state, and then imagine. Now it'll go through a sequence of states. So let's say the next one after Q1. It reads the first symbol of the string S, and let's say the transition table, the transition function delta, tells it to go. The next state will be Q3, and then it reads the second symbol coming in, and the next state after that, let's say, is Q20 or whatever, and then after that Q9, and so on, right? Until eventually it comes to, it's read all the symbols in the string S. So in other words, it's read n symbols. Okay. Well, we're coming to anyway. So let's say the final state that it's left in after finishing reading the input string S is that final state is Q13, and since S belongs to A, this string here gets accepted by the machine M. Okay, so in other words, Q13, the final state has to be an accept state. Right? Has to be, because S belongs to A. S is a string that gets accepted by the machine. Has to be because it's one of the strings that belongs to the language A. All strings in that language are accepted by the machine. Okay, so now let's assume that the size of the string is n. Okay, and this string here, now here's where we come back to it. I mentioned a bit before. So we're assuming this string has length at least p, okay? And its actual length we set is n. And therefore n has length, or n is at least p. So n, in other words, n is greater or equal to p, right? No, n is greater or equal to p. That's said here and here. You put these two together and you deduce that n is greater or equal to p, right? Now, how many states did we go through as the string s went through the machine, got processed by the machine? Well, there'll be a state change for each symbol that gets read. There'll be a state change. Okay, but you start off in your start state Q1. So the total number of states we're talking about will be n plus 1. Okay, n because of the n symbols. You get n state changes, but also your initial state Q1. So in total, you'll have n plus 1 states. Right? And here they are in sequence. You know, time's going this way from left to right. So you started from Q1, then you went to Q3, Q20, Q9, ... and you end up in the final state Q13, which is an accept state. Has to be, right? So that's the sequence of states that your machine goes through, right? Okay, so how many of these are there? How many states are there in the sequence? N plus 1, right? N plus 1 of these. And how many states are there? Well, p. Number of states, remember, we chose p, little p, the pumping number. We chose that to be equal to the number of states in the machine, right? So, so n, hold on. Yeah, so we have n plus 1 of these. Now we know that n is greater or equal to p because of this. Therefore n plus 1 is greater than p. Follow that? That's essential, what I've just said. It's critical to the proof. Right? Yeah, I'll go through it again. You have n plus 1 states here. Okay? We know that n is greater or equal to p from this. Right? And this. N is the size of your string. Okay? And its length, n, is at least p. So n is greater or equal to p. Right? So n plus 1 will definitely be greater than p. Okay? So n plus 1 is greater than p. But what is n plus 1? What's the number of states in your sequence? There's n plus 1 of them. Right? But what's p? P is the number of states, period. Okay? But n plus 1 is the number of states in this sequence, and p is the number of states that there are in the machine. Okay? Now put those together and you can deduce, if you think about it, that means that this sequence of n plus 1 states has to have at least one state that's repeated. Okay? So, does that seem reasonable? I mean, if every state were different, you would run out of states after n, but we have n plus 1. We have n plus 1 states in this sequence. So at least one of those states must be a repeat, has to be. And that's an example of the pigeonhole principle that I was talking about a bit earlier. Okay, so that sequence of states must have a repeated state. Okay, at least one has to be. And it's saying it's an example of the pigeonhole principle. And what is that? What is that?